everyone. My name is James. Fantastic. Okay, so I spoke at PyCon Spain last year, and I gave a talk about generators. And this is one topic that I've been speaking about for a while now. Each year, I try to find a new aspect to generators that is still compelling, so that you don't keep hearing the same talk over and over again. I will say that there is some material from this talk that's similar to last year's talk. The title is a whole lot sexier. But let's get started. So we're at PyCon Spain. It's Sunday, November 9th, and I'm James. The materials for this talk and materials for most of my talks are on GitHub. Go to github.com/DUTC. A lot of these talks are in gists on GitHub, so you can go to gist.github.com/DUTC. If you want to get in contact with me, you can send me an email at james@don'tusethiscode.com, or you can follow me on Twitter at don'tusethiscode. This is me right here. Every time I come to PyCon Spain, I get a bunch of new Twitter followers, so it's one of my favorite events. I really need to start putting some of these notes online in blog form. I do have a blog, seriously.don'tusethiscode.com. I haven't updated it in a while. I also have, I'll tell you, I use this for everything. So I have another web server for some temporary projects called really.don'tusethiscode.com, and it just keeps on coming. It's really great. I'm on IRC. So if you're on the Pound Python channel or Pound Positive Python or Pound NYC Python, you can look me up as DUTC. Somebody actually name-checked me yesterday. They said somebody was asking about instance check, and I gave a talk about instance check about a year or two ago at PyTexas. And they said, oh yeah, this is by the guy, and he's on IRC as DUTC, and he often gives talks about code that you shouldn't use. So eventually you're getting your name out there. Sometimes I'll be online as DUTCH. The H there, I'm from Texas, so could be interpreted as don't use this code, Haas. So most of my talks follow about the same pattern, so I'll continue with an introduction of myself. I run NYC Python, which is, by our reckoning, the world's largest and most active Python meetup group. We call ourselves the world's largest Python meetup group because we have 6,000 members. And we call ourselves the world's most active Python meetup group because we have anywhere between 3 and 4 events every week. So we have 2 study groups on Saturday and Sunday. We have office hours every Tuesday. And every other Thursday, we have talk nights for about 100 people. And we usually have these booked out pretty far. So our next one will be on comparative web frameworks at Syncano. Yeah, it's going to be a fun event. In addition to that, some of these links didn't come out quite right. In addition to that, our meetup group, or the folks behind our meetup group, put together a conference this year called PyGotham. It was in August. It was our version of PyCon Spain, localized to New York. It was a really cool conference. We had 65 speakers and 350 attendees. We're planning to do it again next year. It would be amazing if any of you could attend or speak. It was a really, really cool conference. Separately from both NYC Python and PyGotham, I also ran my own conference last year in March for people in my field. I work in quantitative finance, and I wanted to create a platform for people who are interested in the use of Python in finance to come together and share what they worked on. So it was called Python Quants, and we had a small speaker lineup, but it was a real success. We had some real quants. We had people talk about portfolio optimization, about high-performance American option pricing, interactive financial analytics, a lot of really cool talks. And it was such a success that we're planning to do this again at the end of this month on November 28th in London, partnered with Paul Wilmot's CQF Institute. So it's going to be a really cool event. There are online tickets. So if you're interested in learning more about quantitative finance and how it applies to Python, or how Python could apply to quantitative finance, I encourage you to look it up. It's at forpythonquants.com. And you may wonder what it is that I do in my day job. So all of these threads are somewhat related. I work with a company called the Python Quants, and we advise hedge funds, banks, financial groups on how they can use Python to solve analytical problems. You can think of this as the intersection between big data, programming, Python, and finance. Pursuant to that, I give a lot of talks. And so I like to put this on screen just to remind myself how much I've traveled this year. So this is the list of talks that I've given this year. You can see we're almost towards the end of the year with PyCon Spain right here. It's been a wild year so far. This is one of the events that I was really, really looking forward to this year. So I'm really glad to be here. Maybe next year I can give 7 talks. I don't know. I gave a lot of talks at PyTexas this year. But to continue on, I like to start my talks with a little joke, just to warm up the crowd. I found that when I gave a talk in Germany, this was absolutely necessary, and it didn't work at all. I find whenever I give a talk in Spain, the crowd actually has warmed itself up for it. So let me take you up just a little bit higher, take your energy level just 1 notch higher, and I'll ask you, have you all heard about those new whiteboards they have in classrooms? They're remarkable. And I have one piece of advice for you. Oh, actually, I have one more. What did, and this one's really, really bad. What did the green grape say to the purple grape? Yes, breathe, man, breathe. Okay, fantastic. So you're warmed up and ready to go, and we're going to talk about generators. So each of my talks, I like to give some broad themes, just some things to think about that aren't just down in the weeds details. One of the themes of this talk is code in motion. So when we're analyzing and talking about code, we often talk about it as a static quantity. We often say, well, this code is elegant, and this code is inelegant, and this code has this problem, and this code doesn't have this problem. But I think we neglect that writing code is part of an engineering process, and engineering processes are dynamic processes. Namely, you'll write some code, and then something's going to change, and that code has to adapt to that change. And our analyses often forget how our code adapts to changes. I think generators are a very interesting technique to model problems that you run into that adapt very nicely to changes. I think that another thing is sometimes we come across a programming problem, and it's kind of like a knot. And sometimes we'll pull on this side of the knot and pull on this side of the knot, and we might be able to get almost a simple thread out of it, but not quite. Or maybe we even knot it up further. And I think every so often, we'll work on a problem, and an idea will come to us, and that idea will just unravel knot completely. With just the right frame of mind, or just the right conceptualization, what originally is a very difficult problem becomes a very easy problem. And I think that generators provide you a very different way to think about the way that you model your code, a very different approach that can take what are, without generators, a very hard problem and make them very easy. And more formally, I like to talk about what is programming, but I think those are the 2 parts that I'm most interested in conveying for you guys today. So one thing that is not covered, because I didn't want to repeat myself too much from last year, was what a generator is, the motivation for using a generator. People talk about generators as a mechanism for gaining efficiency. There's some theory behind generators. There's theory about coroutines. I think that Python is a more practical language, and so if you're interested in the theory behind generators, there are programming languages out there that try to explore that a lot better than Python. I think Python is using this as an applied technique, a useful technique. And one last note, if you're following along, I'm using Python 2 for this talk, and I have a couple of future imports just to make everything work. So if you have any questions about why this works or doesn't work, just bear in mind that there's this future import. And this is only mildly relevant. The next slide. So to start, the topic of this talk was generators will free your mind. And I think the best way to motivate how generators can really change the way you think about code and free your mind is to tell you that functional programming has already done this once. So who in the audience here knows what I mean by functional programming? Everyone. Fantastic. And let's take a look at a very common problem, a somewhat synthetic but very common problem, and see how functional programming really changes the way that we think about that problem and takes a very complex problem that gets knotted up and turns it into something very simple. So let's say that we're tasked with building some system that reports on something. And in this case, it's going to report on the profit that a company makes. And the company makes profits in a lot of different areas of the world. So it has profit in the US, in the UK, in the EU, in Central America, and so on. They don't have any profit in their Antarctica business. And their profit in each business is somewhere between -$4 million and $4 million. The actual numbers aren't that important. Somebody says, OK, let's take this data, just in this dictionary, and report on it. So print it out to the screen. Simplest thing ever. So you write, your job is to write this output function. And the output function takes in the data and prints it out to the screen. So you just iterate through all the items, and you print them out. And you say, you know what? I'm amazing, this is why I get paid the big bucks, and you go home. And you think you're done. But this never, ever happens, because the very next day somebody comes to you and says, well, you know that thing that you did for me yesterday? I want you to add just this tiny feature. It's not quite complete. You're not quite done yet. And they say, look, I can barely read this on the screen. I mean, the numbers are right next to each other. Can you at least align them so it's a little bit easier to read? Simple task. It'll only take you an hour to do. So you think about this and you write some new code. And your code transforms from that 3 lines to these 4 lines. And in these 4 lines, you figure out what the maximum length of any one of these left column regions are. And then you figure out how much you have to pad, and you pad it, and you print it out nicely. And you say, amazing, I'm done. I never have to touch this code again. It's fixed. And somebody says, well, you know, we kind of want to have a slightly different format with that. We want to have commas separating them. You know, we want to make it look a little bit nicer. The boss can't really read it in that fashion. So you say, okay. What I'll do is I'll create a little line format, and I'll put in the proper formatting. And they say, we also kind of want you to store this to a file, because in addition to printing to the screen, it's useful to have in a file. So you say, okay, I'll put a file name parameter in there. And if the file name is none, I won't do anything. But if the file name is provided, I'll open a file and I'll write it to a file when I print it to the screen. Are you happy yet? And of course, they're never happy. Because they say, okay, you printed it to the screen and you put it into a file, but can you also log it on just a standard logger, just so that if there's any problems, our ops guys can figure out what was going on there? And you say, okay, I'll add in a little parameter called toLog, and I'll set it to true or false, depending on whether I want to log it or not. And if I've set it to true, I'll just call my logging.info and print it out to my log. Are we done yet? Of course not. Because somebody says, well, you know, the boss is used to seeing numbers in Excel, and so he likes the Excel format where negative numbers have parentheses around them. So can you do that as well? But only some people like that, because when we pass it to the accountants, maybe the accountants like another format, because they feed it into a back office system that expects negative numbers to have a negative sign in front. So you say, okay, I'll add another flag. And the flag will be called accounting equals true or false, to show if I put this in this accounting format, this Excel format, or not. And if it's in the accounting format, then if it's a negative number, I put parentheses around it. If it's a positive number, otherwise I just print out the number as is. And you can see here, this is in the accounting format. And unfortunately, we're still not done, because some boss doesn't really want to log into his computer to do this. He wants it emailed to him. And email to him is a little bit different, because you probably have somewhere in your system a send email function that takes a to, a CC, a heading, and a body. And that body is usually the entire body of the email. So you can't just stream it. With the log, you can just stream line by line. With the email, you have to collect all the lines and then send it off to the function. So now you have to indent everything over 1. And when you indent everything over 1, you capture each line. So you have to create a little bit more state here to capture each line. And at the very end, you have to say, if we're sending it to an email, you join it up and you call this email function. And of course, there's going to be even more parameters if you're really doing this, because you'd have to add in a to and a CC and a subject line. And you could think, what does it mean for the combination of parameters where you say to email equals false, but you provide an email address in the to line? What does that even mean? Does that mean that you wanted to email? Does that mean you shouldn't email? It's not even clear. And you think, this is absolutely nuts. I have to do this better. And so the first thing that you do, or this I'll skip over because you really don't need to look at that, but the first thing that you do is you think, how can I make this simpler? Well, I have these separate tasks, but they're all doing the same thing on my data. So what I'll do is I'll apply a little bit of functional programming. And instead of having these 15 different modes, like to email, to log, to file name, I'll just pass in one function called write. And write could be maybe the print function if I want to print it to the screen. It could be logging.info if I want to log it. It could be email if I want to email it. It could be anything. And I'll pass in some templates, so you can decide how you want to template them. And I'll use a little bit of object orientation, so that when you want to format them in different ways, you can just wrap the numbers in a number that knows how to format itself correctly. And here, you have the exact same code that you had before, but now it's 4 lines long, and it can do even more than you could do before. And the problem has suddenly been unraveled with just a small application of functional programming. Instead of hard-coding all those modes, you just say, I don't care about the modes. You give me a function, I'll give you some lines, you figure out what to do. And now you can email it, you could do anything you want with this data. So this is my example for how functional programming has already freed your mind. You can see that this code is much simpler and also much more flexible. This code has allowed you to free your mind from presuming modalities. In the first code, your parameters had to list all the different modes. And you had to worry about what happened if they have this combination of this mode and this mode and this mode and this mode. Here, there are no modes anymore. You pass it a callback, I call a callback, that's the end of my responsibility. Any modality that's included in the callback itself is your responsibility to test. For me, I just have to make sure that if you pass me a function, and that function takes a line, I pass that line off to you, and that's the end of what I have to take care of. My API internally has been simplified dramatically. Instead of having 15 different parameters, I now have 3. And I think we've all dealt with incredibly complex APIs. If any of you are data scientists and have used pandas or matplotlib, these are libraries that have accrued so many functionalities over time that when you look at the number of parameters, look at pandas read CSV and how many arguments it takes, it's nuts. Because it does a lot, and it's accrued all of this functionality over time. But we can see, in some cases, just the right application of functional programming removes that entirely. The API is now very simple, and it's hard to misuse this. In my original example, I could have provided maybe a toEmail equals false, but I could have provided an email address. What does that mean? In this case, I provide a single function, and the ways in which I can get that wrong are very limited. Because as long as my function can accept one parameter, that being the line, and can be called multiple times, the rest of it is up to my implementation. There's much less surface area for me to make a mistake. And more importantly, I think, this has empowered your users. So now, when you come to me and say, well, I want to write this to a database, I can say, great, write a function to write it to a database, I'm going to go home. Whereas before, it was now my responsibility to add that functionality into the code, right? And I was on the hook for adding all of those different modes. Here, you are now empowered to do whatever you want. You can write this data anywhere you want. You can do anything you want. I'll provide to you some functionality that you're asking for me. And from there, you can do anything that you want. I will note that pure functional programming has probably further freed your mind, although I won't talk about pure functional programming in this talk. One thing that I think is very important to note is that Python is a very practical programming language. It wasn't built upon the same theoretical foundations as a language like Haskell or a language like OCaml, but it was a language built upon collecting tools that were useful for getting real work done and putting them together in a consistent place for you to apply to solving real problems. Pure functional programming is, I think, a very, very interesting topic and one that's worth exploring. Although, just like Python allows you to do functional programming, but doesn't really make any comments one way or the other about pure functional programming, for generators, Python allows you to do generators, but some of the mechanisms around generators are not as fleshed out from a theoretical perspective. So let's take a look very briefly at what a generator is and what a coroutine is. This is just a function, and it's called fib, and it's a very common function. I'm sure we've all been in an interview situation and asked to write it. And the function takes two numbers, some kernel, and some number to count up to, and it counts up to that number and creates elements of the Fibonacci sequence. So you can see when I call fib, it gives me the first 10 Fibonacci numbers, 1, 1, 2, 3, and so on. And I'm going to write another function called ratio. And ratio takes some list, and it takes subsequent elements and finds the ratio between adjacent elements. So the ratio between 1 and 1 is 1. The ratio between 1 and 2 is 2. The ratio between 3 and 2 is 1.5, and so on. And you might wonder where this is going, but this is one very interesting thing about the Fibonacci sequence, which is it converges to phi irrespective of what numbers you start with. So you can start with any two numbers, and the ratio of subsequent terms converges to the golden ratio. And one really neat thing about the golden ratio is the golden ratio is about 1.6, and the conversion between kilometers and miles is about 1.6. And so if you ever found yourself needing to quickly convert between miles and kilometers, you could use your knowledge of the Fibonacci sequence to do it pretty quickly. So that said, about 3 kilometers is 2 miles, about 5 kilometers is 3 miles, about 8 kilometers is 5 miles, and it's an easy way to do the conversion because that ratio converges. And as you look at larger and larger numbers, you get more and more accurate. This is the generator formulation of it. So this code is the same as the first code, except instead of formulating the Fibonacci sequence as a function, I formulate it as a generator. And there are some meaningful differences. From a formal perspective, from the form of the thing, the difference is there's no return. There's now a yield. Another formal difference is I'm not keeping track of any internal state explicitly. In the first example, I had a list, and I'd append items to the list and return the list. Here, there's some state being tracked, but it's being tracked implicitly on the local variables. And very importantly, this formulation is lazy. So I'm only calculating values as you ask for values out. I'm also not performing, so that means I'm not performing the entire calculation at once. I'm performing the calculation as it is desired. So with this formulation for the Fibonacci sequence, let's say I want the first 10 Fibonacci sequence. I'll go into the itertools module, which contains a lot of helpers for dealing with all sorts of iterables, such as generators. And I'll take the Fibonacci sequence. This is now an infinite sequence of numbers. I'll take the first 10 numbers, print it out to the screen. I get the exact same functionality. But let's take a look at what I can do with that ratio. So I talked about itertools, and itertools is a collection of tools that are very, very helpful for dealing with generators. This is a little helper that I find that I can write from memory now. It's very simple, but what it does is it takes some iterable, and it gives you pairs of them. So if you give it the numbers from 0 to 9, it'll give you 0, 1, 1, 2, 2, 3, 3, 4. It'll give you pairs of them. And then I can just calculate the ratio using that. I can build up these building blocks. I can calculate the ratio as the pairs of the number from my sequence, the ratio between the two numbers. And so you can see I now have the ratio of my numbers. And if I want to calculate phi, I can use a generator. I can use a list comprehension to calculate phi, and I can show that this converges. So that's what a generator is from a formal characteristic. I think the things to make note of is that it's lazy, that which means it performs the computations as you ask for them, that it ends up being a lot simpler, that it's a little bit more theoretically pure in the sense that instead of producing a list with a fixed number of elements, I'm producing just an infinite sequence of Fibonacci of numbers from the sequence, and that the code ends up being more composable. So let's talk about how generators can really free your mind. I think that generators can free your mind from presumptions about how the code that you're writing will be used. When you're writing code, you may have in your mind how you think that it'll be used or how you expect it to be used, but I think you don't want to take on too many presumptions about how it will be used, because this is code that will go through your organization, and people who you may have never ever met may be using this code. And the more that you presume about how they want to use the code, the worse their life is going to be, because they may have to work against those presumptions. So let's take a look at our Fibonacci sequence in the form of a function. One presumption that I made when I wrote this out was I said you want the first 10 Fibonacci numbers. So I said you want the first 10 or the first 20 or the first 30. But you can think, when people ask this question in an interview situation, sometimes they say print out the first 10 Fibonacci numbers, and they say print out the first Fibonacci numbers that are no greater than 10. And here we have two separate formulations. This one prints out the first 10, and this one prints out the first that are no greater than 10. So here, I print out all the ones, the first 10, and I print out all the ones up to but no greater than 10. And if you look at these two formulations, I had to pick one or the other to write. And I had to presume which style that people wanted. And maybe I presumed wrong. And if I needed to support both of them, imagine how complex the code would become to do the same thing that my simple Fibonacci here can do. So if I start with my generator formulation for the Fibonacci sequence, I produce an infinite sequence of them. And then if you want the first 10, you can use islice from itertools to get the first 10. If you want the first that are no greater than 10, you can use takewhile from itertools to take while they're less than 10. And if you come to me and you say, I want Fibonacci sequence, the first 15 that are between 5 and 100, I can say, fine. Go into itertools and take out dropwhile, takewhile, and islice, and you can build that yourself. Whereas if I had to write this in my function, imagine how complex it would be to support even these two predicates. To even combine these two into one function, think about how complex it would be. And think about how many times you're presuming how your code will be used, you're wrong, and then you have to start adding more and more blocks and start indenting everything over. We saw this with the email example at the beginning. Additionally, I said that generators are lazy, which means they provide computations to you only as you ask for them. Here we have a simple little function called query, and all it does is it produces some number, but it sleeps every time it produces a number. Let's say we wrote this as a function, and we collected intermediate values, and we returned that. How long would this function take to execute? Well, it would take 10 times 0.1. It would take 1 second to execute. What if I only ever wanted to look at the very first value? I would have to pay 1 second of time for you to execute the entire bulk of that code before I could look at just one value. If I write this as a generator, I would be making available to you a way to query only one value and only pay for the computation of one value. So here, in this example, I want to look at just the first value. So I'll take the sequence of values it produces, I'll slice out only the first value, and then I'll throw away the sequence. And in that case, I only pay for 100 milliseconds worth of processing time. Sometimes we talk about generators as being a mechanism for efficiency, both memory efficiency and time efficiency. I think one of the most compelling and indisputable ways that generators can provide efficiency to you and your code is not by making something faster, by making it so that you don't have to do as much work. That if somebody wants only part of the computation, they only have to pay for part of the computation. And so even if the computation itself, even if each step is slower than the same in the functional formulation, just by virtue of not having to do as many steps to get the results that they want, the program can run faster. I think generators also free you from some formal presumptions, like presumptions about return type. So we've all been in a situation where somebody said, write a function that does this calculation. And you had to wonder, well, what should I return? If I'm going to return, should I return a list? Should I return a tuple? Should I return a dictionary? Should I return a set? And in some cases, it wasn't clear which of those was the right answer. Notice, in my generator formulations, there is no return statement. I'm just yielding values out. So I no longer have to presume where the values are going to go or how they're going to be used. So let's take a look at 3 simple functions. They're called process. So this one just takes some numbers and it appends it to a list. This takes some numbers and appends it to a set. And this takes some numbers and appends them to a tuple. And in each one of these, we can imagine this being more complicated because I could add maybe some calculation in here as well, or some processing as well. And each one of these may have different implications on a user of this function because they may not want a list, they may not want a set, they may not want a tuple. And depending on how they're using the data may have different meaning. In some cases, they might want to receive that data as a set because they may expect to see unique items. In some cases, they may want to count how many items are duplicated, so they may want the data back as a list. Or they may want the data back as a counter or a dictionary where they have the elements and the count of the elements. And you may not want to presume what you want to give to the various disparate users of your code. So with the Fibonacci example, let's take a look. This Fibonacci example returns a list. And let's say I want to put it into a tuple or a set. And you can see there's some time associated with taking this list and converting it to a tuple, or taking this list and converting it to a set. And you can think that in order to do the conversion, the entire list has to be in memory as you build up the tuple or as you build up the set. So if this is a very big piece of memory, if you're using 100 megabytes of memory for this list, then at some point in your program, you'll have up to 200 megabytes of memory being used to keep that list and the tuple version at the same time, or that list and maybe a smaller set version at the same time. Here's my generator formulation. And I haven't presumed how you use the values. I'm just giving you the values. I'm just throwing them at you. And then you get to put them into a list, a tuple, or a set as you desire. And a nice consequence of it is that it actually turns out to be faster. So it's actually faster for me to say, I don't care how you use the values. I'll just throw them at you, and for you to collect them as we go. And it's also going to be more memory efficient because you no longer have to deal with having 2 copies of the data in memory at the same time. I'll just give you the data, and if you want to start throwing them away, you can start throwing them away. Imagine if you had an enormous, say you had a 100 megabyte data set where there were a lot of duplicates, and there are only 5 unique elements. At some point in your memory, if you're returning a list, you'll have to return all 100 megabytes worth of it, and then trim it down to 5 items. Whereas with a generator formulation, you'll only have to keep enough memory for those 5 items because you can immediately discard the computations as you go. Now, there is, talking about return types, we can also talk about input types. And let's take a look at a simple function called average. And average takes a list of elements, XS. And somebody read that, maybe it would be a good idea to make sure that you're giving me the correct inputs. So they add a little isInstance check at the top. In fact, on Python last night, there was somebody who was asking about whether or not they should be adding isInstance checks like this throughout their code to make it more robust. I know that I've run into code that looks like this, and it's bitten me when I tried to give it something different. So the code itself only requires that you have something that you can sum and something you can find the length of, but they've strictly said, I want a list only. And when you give it a tuple, it blows up. But you can say, well, if you can calculate the average of a list of numbers, why can't you calculate the average of a tuple of numbers? And it doesn't make any sense. So you go to that programmer and they say, okay, I'll improve my code. I'll go into collections or collections.abc and I'll pull out sized. And sized is something that can be summed, and something that can be something that has elements, and we can sum the elements, and something that has a length. And sure, that works perfectly fine. But one of the assumptions that this code is making is it's making that it's making an assumption that you have all the data at you have the data in concrete form all in one place. Because you need to be able to do the sum of it, you need to iterate through every element and take the sum, and then you need to be able to iterate over it again and take the length. Or you need to have something that's sized which has a fixed length. So you may find that in some cases taking this freedom from presumptions may seem a little bit gratuitous, but this is a formulation for average where it makes no presumptions whatsoever about what you pass it, except that it can be iterated over. What it does is it collects the value, and it collects a 1 for every element in the sequence that you give it, and then it sums all the values, and it sums all the 1s, so it gets a total and a count, and it divides the total to the count to give the average. One interesting thing about this formulation is that it works on generators. It works on every concrete type, lists, dictionaries, anything that can be iterated over. It works on any custom iterable. It works on anything where you can iterate over the values. And if this happens to be a stream where you can only iterate over the values once, it still works. So one thing that generators encourage you to do is write your code in a fashion that makes it more robust, that reduces some of the assumptions that you make, or sheds light on some of the implicit assumptions that you may be making when writing your code. I think very powerfully, generators also help simplify your APIs. They remove presumptions about modes and modalities. So you saw in our very first example, we started accruing all these different modes for our code. And I think generators give you a way to encode the same functionality, but without having these endless lists of parameters. So let's take a look at an example of that. One example of that I like to use is this guy here. So we have two functions. One of them represents some data source, so maybe loading from a database. And what it does is it yields random numbers, and it sleeps. So maybe think of this as maybe a database query. You have a cursor, and each time you're looking at the next row, it takes a little bit of time to return the next row to you, and it returns some value. And in this case, I'm just returning random values. And let's say that I have some function called LoadData. And what it does is it performs some calculation on the data that you provide. It's calculating just the average on the data you provide, and appends them to some output data set. Well, by virtue of having this sleep function in here, when I call LoadData on my source, the function takes a while to return. And this may not be acceptable to your users. It may be acceptable that it takes a while to perform this computation, but it may not be acceptable to them that they don't know if the computation is currently running or not. And so you may be tasked with trying to provide a little bit of insight into the running of this function to user. So this function needs to return two things. It needs to return both the actual result, and it needs to have some side channel by which it can convey to the user where you are in the computation, whether the computation is halted or whether it's continuing to go on. And so maybe that's part of some splash screen for some application. Some application is starting up, and you need to say, no, it's okay, we're still loading, just hold on, the application's almost ready. So what do? The very first thing that you might try doing is you might try adding like a little print function in this for loop. And you say, okay, I know how many elements I have, I know what element I'm on, and I'll print out just the percentage that I'm going. And that's really nice. You can print out 0%, 20%, 40%, 60%, 80%, and you might call it a day. But think about this function, this LoadData function. This LoadData function is, well, actually, before I go into that, let me say that you may want to make this a little bit richer, so you might want to say when the computation is begun and when the computation is ended. Because if it stalls at 80%, then the user may still be wondering, is it still computing or not? So you make this a little bit richer, and you add one thing at the beginning saying we're beginning to load, and then you say one thing at the end saying we're done loading, and you give the percentage of where you are as you go. Now that said, you may find that this code, this LoadData code, that's all about just the loading of data and not about anything input-output related or anything UI related, kind of presumes something about the UI. It presumes that this is being printed out to the console. But your LoadData function could just as easily be used in a web page or used in a desktop application, which may want to create a splash screen. So you say, okay, I don't want to create these millions of modes to handle, am I showing my progress text in a console? Am I showing it in a splash screen? Am I doing this? I'll apply a little bit of functional programming, and I'll end up with something that looks like this. My LoadData takes 3 callbacks, before, during, and after. And before the computation starts, it calls one of the callbacks. During the computation, it calls another callback with the state of the computation. And after the computation, it calls another callback. And for the case where you're printing this out to the screen, the callbacks are easy. You print out loading, you print out the % of where you are, and you print out done loading at the end. If you're doing this for a web app, maybe this creates some other signal, or if you're doing it for a desktop app, maybe this pops up the splash screen, this updates the splash screen, and this closes the splash screen. Who knows? But notice, in my use of this, I have accidentally swapped the before and the after functions. And this is one thing that I think is very important about APIs. An API needs to be very careful to prevent users from accidentally misusing it. And in this case, the API has not made itself robust to accidental misuse. You've provided 3 functions, and I've made it very difficult for you to know which function you should call when, or made it easy for you to make a mistake like the one here, where you accidentally print done loading before you're done, and you print loading when you actually are done. And you might think, how can I fix this? Well, I could add some checks, or I could add some documentation, and that's a very good approach. But there's not that many checks you could add to distinguish a function that looks like this and a function that looks like this. You might not be able to tell what the order of them are, but you know for certain that you want to be able to provide some mechanism by which you have 3 blocks of code that are called in a specific order, and you can't screw up that order. Well, that's exactly what a coroutine is. And so if I reformulate this code with a coroutine, and I give it a function called update, the update can always call the start code at the beginning, can always call the processing code in the middle, and can always call the finished processing code at the end. So here I have a much simpler API. Now my LoadData takes one function, one coroutine, and this coroutine forces the order of those 3 functions so that it can't be misused. So that I say, give me a coroutine, and the requirement of the coroutine is it has to be able to interrupt my program in certain ways, or I have to be able to yield control to it in certain ways. This is something that I might be able to test. I could write a little tester function that just kind of checks that the coroutine works in that fashion. And then it's much harder to misuse this code. So you can see that generators and generator formulations make it a little bit harder for you to misuse code. They simplify this API. Now you have only 2 arguments. And we've added a little bit of conceptual complexity in that we have to think, what is a coroutine? How does it work? We may have to work around some of the ways that coroutines work in Python. But we've suddenly gotten something where now I can force an order of a computation while still interleaving other computations in between. So I think an even more compelling example of this is holiday calendars. Or an even more compelling example of generators in general is holiday calendars. So here I have the holiday calendar for 2014 for the Japanese financial markets. And you can see they take a lot of holidays. I mean, look at that. They have Christmas, they have Boxing Day, they have a lot of holidays, a lot of banking holidays in Japan. In fact, they have so many banking holidays in Japan, they just started numbering them after a while. So it's like banking holiday 1 and 2. It's great. And they celebrate whenever US financial markets are closed, their financial markets are closed. So they'll celebrate US Memorial Day and UK Spring Bank Holiday. It's fantastic. Actually, I imagine probably working in finance in Japan is very difficult. But at least they have a lot of holidays. Let's take a look at a function that we've seen in probably every code base we've touched, which is calculate nth business dates. It's a very useful thing to be able to calculate 1 business day ahead, or 2 business days ahead, or 3 business days ahead, to skip holidays and to skip weekends. And almost invariably, the code will look something like this. You'll have 2 while loops, one here and one here. The outer while loop will tick days ahead. The inner while loop will push them past weekend boundaries. So this will say add 1 date, and this will say while that date is a weekday or it's in the holidays, push it ahead 1 day. And then there'll be some decrementation of how many business days you want to go ahead, and you end up with code that can be used in this fashion. We're starting from 2 days before the 4th of July, so July 2nd. We want to go ahead 2 business days, so we go 1, we skip the 4th of July, we skip the 5th of July, we skip the 6th of July, and we go to the 7th. I use this, by the way, because I presume that no matter where I give this talk, everybody knows that the 4th of July is a very big holiday in the United States. And one thing that can be interesting about this is, what if I want to find the next 3 business days? So I want to go 1 business day ahead, 2 business days ahead, and 3 business days ahead. Well, I'm re-invoking this double loop every time. And maybe one of the parts of this loop, maybe there's some database query to get the next holiday. So maybe this inner loop is a little bit slow. And you can think, I'm repeating this computation multiple times, right? I'm starting from the same point, and I'm skipping this date, this date, this date to get to the end, and I'm doing the same skips, I'm doing the same skips. There's a lot of redundant computation here. And there's a lot of redundant computation because the way that I've modeled it is too eager. With generators, I can model this a little bit more lazily, and I can avoid some redundant computations. But I can also gain some very nice properties out of this. So the very first generator formulation I'll give you looks like this. Instead of giving a fixed number of business days ahead, let's just create an iterator that gives an infinite number of business days going forward. So all this does is it yields an infinite number of business days forever and ever and ever. And if I want the next 3 business days, I just call next on it 3 times, or I can slice into it 3 times, and I'll just go through each loop to skip each of these holidays once. And if I call next again, I'll get the next business day after that, and the next business day after that. So the generator allows you to encode state in a very nice way to allow you to avoid redundant computations. But let's see how I can take this example a little bit further and see how we can unravel some of the problems around writing code. So let's say I want to make this a little bit more general. I want to look at both business days going forward and business days going back. Well, I can apply a little bit of functional programming, and I can give it an argument called direction. And direction is either an addition or a subtraction. So instead of strictly adding 1 day in each of these loops, I just call direction with the number of days I'm adding, forward or backwards. So now I've taken the exact same code, and instead of giving n business days ahead, it can now give n business days ahead or n business days backwards. In fact, I could take this even further, and instead of hard-coding the number of days forward or the number of days back, I could just make these lambdas, and I could simplify these lines of code into these lines of code with 2 parts. So I have date count, which is similar to count in the itertools module. It just gives you subsequent days going forward on some pattern. So if you give it NBD, next business day, or actually this should be next day, then it'll give you days counting 1 ahead. If you give it previous business days, it'll give you days counting 1 behind. You can give it a step of 2 days or 3 days or anything that you want. Now think about this. This is a really easy function to test, isn't it? Because all it does, its entire contract with you, is you say, starting from this date, give me days going forward or days going back according to some pattern. So give me days stepping 1 day at a time going forward or days stepping back 1 day at a time. Days stepping forward 2 days at a time or days stepping back 2 days at a time. You could probably enumerate all the common possibilities and test this with a couple of lines of code. Just a couple of asserts, and you'd be done. There is state here, but that state is encoded in such a way that it doesn't explode the number of unit tests you'd have to write. In fact, all you have to do is test this guy in isolation, and you can say, OK, it works perfectly. And then you have business dates, and business dates just takes a starting date and takes a direction to go and some holidays, and it just counts through days from that starting date, going in that direction, and just skips the holidays. So I've actually taken this piece of code, split it into 2 parts, and it's not only shorter, but easier to test, and each of the parts can be reused. So now I can start at the 2nd of July. I can say, go for previous business days. I create a count that says, OK, I'm starting from this date, and I'm going backwards. And then I just iterate through that count and say, if the weekday is not in 5 or 6, it's not on Saturday or Sunday, and the date is not in the holidays that I provided, skip it. And so now I have 2 lines of code here and 4 lines of code here encoding the exact same functionality. But now you can do a lot with this. You can say, what's the nth business date, count using this business date format, counting 2 days ahead, skipping 3 days ahead, and you can do it very efficiently as well. But let's take a look at maybe a more realistic situation where some of these business dates are stored in an SQL database, a holiday calendar, as you will. And there's some time cost to actually querying the holiday calendar in order to get the holidays back, in order to calculate what the holidays are. Well, what I can do is I can use the exact same code I have, and I can just replace this. I have just a dictionary with all the holidays in it. I can replace the holidays with some lambda that just takes a date and says, is it a holiday or not? I can encode the calculation for whether a holiday is a holiday or not with just another generator that says, OK, if I've read up to today for my internal state of the holidays I've loaded from the database, and the holiday is today, say true, Otherwise, keep reading to the database until you get to the next holiday. If you've passed the date you're dealing on, stop and say false. So all we have here is now a very interesting and very efficient formulation for this problem. You'll only ever query from the database exactly the holidays that you want to look at, based on exactly the holidays that the user asks for. So if they say, tell me the next 3 business days starting from Christmas, you only query your database for Christmas and New Year's, or maybe not even Christmas and New Year's, depending on what the holiday is, but you only query your database for one holiday. You don't do extraneous database queries, because the code has suddenly now been able to model exactly what your intention is and can translate that into lookups into a database exactly based on your intention. And now you can do all sorts of crazy stuff. You can do any business date formulation. You could say modified next business date. And when you go into the difficulties of business dates, you'll actually see that there are a million different conventions for what it means to skip a business date. When you get to the edge of the month, what does that mean? Do you skip forward? Do you skip back? You can encode all of that very easily, and you can test each of those pieces in isolation without having to test them, without having to test the quadratic complexity of all of them against all of them. The quadratic complexity of when you combine all of them together. So let's take a look at my last example. And this is an example that we saw very briefly last year, but I think it's one of the most compelling examples, and I've fleshed this out even more. Another common interview question is count change. So somebody says, you have a vending machine and you put in €5, and the soda costs €1.72. How much change do you get out of the vending machine? And what you might think about the change is you might say, okay, here's my naive way to do it. So I say, okay, here's all the denominations I have. These are US denominations: $1, 50 cents, a quarter, a dime, a nickel, a penny. You have some list with all the coins you're collecting, and you say, while any one of these amounts is, while the amount that you're counting up to is greater than any one of these denominations, you append that denomination, and then you subtract that from the amount. So you start with $1.72, and you say, okay, I have a dollar bill. Okay, now I'm looking at 72 cents. Okay, I have a $half, that's 50 cents, so now I'm looking at 22 cents. Oh, I need two dimes for that. I have 2 cents left. I need 2 pennies, and I'm done. And so you end up with this. But what if somebody says, I want you to make this example a little bit more realistic? In the previous example, you presumed that you had as many dollar bills and as many nickels and as many quarters as you wanted. But in a real change counting situation, you may only have a limited number of coins of each. In this variation, you have only 5 coins of each. You have $5 bills, 5 half dollars, 5 quarters, 5 dimes, 5 nickels, and 5 pennies. And notice the code is beginning to explode in complexity again, because you have to add another little loop here to say if the denominations, if I've already counted too many nickels, I can't add another nickel. If I've already counted too many pennies, I can't add any other penny. And you can see the addition of this predicate now makes this code much harder to do. And there's no way for you to encode this on the back outside of this, right? There's no way for you to use the original function and then make some modification to the output that it gives you to make it valid. You have to encode the complexity of having a limited number of coins in this function here. And you can see it's starting to become a little bit messy. So here we have an example of this though is a little bit nice because we can actually control the number of denominations we have of each. So here we have an example where we have 3 50-cent pieces, 10 dimes, and 20 1-cent pieces, and you can see the change that you count is much different. You can't count change with nickels because you don't have any nickels. And you can do the same thing with, you can try any variation of this. But when somebody comes to you and they say we want an arbitrary predicate, you may find that it's impossible to encode. So I'm going to show you the generator formulation of this. And I think this is going to maybe change the way you think about how you might model this program. So let's think about the core of counting change. Counting change you might call as a greedy algorithm. And I think greedy algorithms are one of those things where the formal term for this is dynamic programming. And I think the only thing anybody ever remembers about dynamic programming is optimal substructure, which is a word that means something, and the greedy algorithm. But essentially what we mean is that we can find an optimal solution for a problem by making locally optimal choices. So if we make the best choice given the information we have right now, in the end, the result will be the best choice overall. Unlike many things in our lives, change counting is actually greedy in the sense that choices that you make in the moment can sometimes be the best choices you can make over the entire course of the algorithm. So what is a greedy algorithm for change counting? Well, you imagine that you have a register with coins going down, and you take as many coins from this as you can until you stop. Then you take as many coins from the next part of the till until you stop. Then you take as many coins from the next part of the till until you stop, and so on. So you'll take as many dollars as you can, as many 50-cent pieces, as many quarters as you can, as many dimes as you can, as many nickels as you can, until you stop. And that's all this does. This take while says, as long as this predicate is true, sorry, you have your items, so you repeat your items infinitely, or you repeat each one of those items infinitely, and as long as the predicate is true, you keep taking from those items, and then you chain it all together to make one big list. And that's all this is. So what's the predicate? Well, the predicate for counting up would look something like this in a generator. So what you do is you say, I'm going to take values until I exceed the maximum. So you have some internal state, you have some number you're counting up to, and you say, if state plus some value that I'm asked if I can take is less than my number, I add that to my internal state, I say true, otherwise I say false. So what this predicate says is, each time you call it, you're given a value, and it'll say, well, based on my internal state, can I take that value and not overshoot the number I'm aiming for, or not? And it'll say true if it can, and add that to its state, or it'll say false if it can't. So let's actually use this. We'll create some amounts. So we'll create 5 amounts, and these are in pennies, so we'll create 5 amounts from 0 to $10, or 0 to 10 euros. And we'll have denominations, 1, 5, 10, 25, so these are American denominations, 1 penny, a nickel, a dime, and so forth, and we'll use it. We'll create our predicate, we'll call our coins, and we're done. So we have 2 lines, plus these, I'd say about 10 lines there, and we've encoded the entire problem. And we can pretty print them, so we have a little bit of code down here to pretty print them. I put an enormous amount of effort. I put more effort into pretty printing them than I put into writing the original code, so that you could see, look how nicely it lines up, and you have the right cent piece and all that. So there you go. But the really cool thing about this is, let's think about this algorithm of counting up to get to something. What's the other case where we find this? Converting to and from Roman numerals is the exact same problem, which means I should be able to use the exact same code to apply to the exact same problem. But before we look at that, I want to look at the more complex predicates. So let's say we have a more complex predicate, some constraint. All I'm going to do is in my predicate function, I'll add in a lambda that takes a constraint. And in the default case, the constraint will always say true. The constraint it'll take is it'll take the value you're looking at adding and all the values you've already added, and you're done. And so in order to encode the I only have a set number of coins constraint, my constraint will be, these are all the coins I've added so far. This is the next coin I want to add. And it'll say, for all the coins I've counted so far, create a counter. Look up the coin that you're thinking of adding. If it's less than 2, go ahead. If it's greater than 2, then you've exhausted and you can't add anymore. So here I have my basic predicate. Well, think. We could add any predicate whatsoever, because we have all the state that we need, which means we could add a predicate here that says, only pick pennies if you haven't picked any nickels. Think about how hard it would be to write into the original formulation using functions to say count change such that the user can define combinations of, you can't pick pennies if you've picked nickels, but only if you pick dimes on a Tuesday. There would be no way to do that, right? And if somebody came to you and said, we want you to do that in your code, you'd throw up your hands and say, that's impossible. It's going to make it impossible. This formulation here allows the user to add any random predicate that they want. They could say, it's Friday, so only give them dollars and pennies. It's Thursday, so give them 3 pennies that we have in the till and make sure that we have at least 2 pennies left over when we're done, right? You can do any constraint and just combine the code to get there. And so exact same as before, we create our predicate, given our new constraint. We call our greedy algorithm on our denominations and our predicate, and we pretty print it. So we have 3 lines of code that can do something very flexible. Now, in our Roman numeral situation, notice we have the exact same lines of code as we had originally. We have a predicate and a greedy, and we have different denominations, namely this, and the pretty printing is a little bit different, but now we've reused this code for a completely different problem without having to change it at all. So we can see 2 ways that generators have fundamentally changed the way that we model the problem and fundamentally changed how we can use this. 1, we can take code that we never expected to use on a totally different problem and apply it because the code is now focused just on solving that one problem. How do I greedily count up to a number given some denominations, given some items that I can combine. And whether that's change or whether that's Roman numerals and Arabic numerals, it doesn't matter. Additionally, we can take one little outlet that somebody's given us for complexity, namely to be able to provide a constraint on how we count up, and we can employ any arbitrary constraint that we desire. And we can do that entirely without having to write any code, without having to ever change the library code we originally wrote. So any user of this function can use this function in any fashion they want. So I think that this is, for me, one of the most compelling cases for how generators can free your mind, how they can change the way you look at problems. And once you look at that problem a little bit differently, it unravels. And suddenly you can do so much more with so much less code. So I hope that through this presentation, generators have freed your mind. My name is James Powell. I would encourage you to all go in peace, and I have to say, I've really enjoyed the conference this year. I'm so glad that I was able to make it. Thank you so much.
So, any question?
Is anyone unconvinced? Is anyone convinced? Yeah. And I think so last year what I talked about was more kind of the how generators work and some toy examples of how you can use them, and I used this example as well. But I think what I was trying to aim for this year was when you write code with generators, it's not just about making your code a little bit faster or saving some memory here and there. It's about finding totally different ways to model the code, totally different ways to approach the exact same problem. And if you can find just the right way, then suddenly what starts out as a very hard problem, like our original reporting example, suddenly becomes trivial, almost impossibly easy. And really think about what you're doing when you're writing this code. I mean, you have to adapt to requirements, and you can see that functional programming and generators can adapt to requirements very easily. You have to be able to verify that your code is correct by testing it, and think for that original function with those 7 parameters, how hard it would be to test that, and how many different test cases you'd have to write, and how easily it would be for you to accidentally forget one of those test cases. And think about, even for this fairly complex generator example, how easy it would be to test it. You test that the predicate works in isolation, you test that the counting up works in isolation, you test the greedy algorithm works in isolation, and you're done. And each one of those is this almost mathematical entity that you can test in isolation, and you know the combination of them is going to work. So that's what really gets me excited. Gets me really excited.
Hi, you were using a decorator, I think, pump.
So when you look at any library that uses generators like Twisted, you'll see one of the unfortunate things in Python is that the syntax of generators is a little bit ugly. So you may have run into an error which is can't send non-none value to a just started generator. This is one of the limitations of using coroutines. You'll often see in these libraries some decorator called pumped or primed. I think Twisted calls it gen.coroutine, that takes the formulation and just fixes some warts in the syntax. So I didn't talk about it too much. It's just the one papering over of some limitations in the Python syntax for a coroutine. What it does is it gets the generator started so that you can start sending values into it immediately.
Thank you.
So I think we can thank the speaker again.
Thank you so much.
And remember, we have now the group picture.